India lands on the moon. Another Ring Nebula image from JWST. One of the coolest exoplanet videos you've ever seen. And new images of Neptune. All this and more in this week's Space Bites. They did it. On August 23rd, India's Chandrayaan-3 deployed its landing system down to the surface of the moon, and it worked. India landed near the south pole of the moon. This makes them the fourth country to ever land on the moon, and the first lander that's ever gone to the south pole of the moon. And this was tense, because when you think back to Chandrayaan-2, that lander failed. And so all eyes were on India to nail this landing, to learn their mistakes from the previous mission. And they live streamed the whole attempt, which was fantastic. And so you could see both the data that they were getting into mission control. You could see the people who were working at mission control as they were sort of focused on sticking the landing, and then just the excitement and enthusiasm after they landed successfully. Would have been amazing to be in that room and be part of that experience. The south pole of the moon is exciting because we know that there are large amounts of water ice trapped in the regolith as well as in the permanently shadowed craters near the south pole of the moon. And so any future settlement, colony, science station, ideally that wants to live off the land is going to want to be able to tap into these giant water reserves. They can use this for breathable oxygen. They can use this as propellant for their spacecraft. They can use this for water to grow crops and other things. So getting water on the moon is vitally important. And this is the system that's going to help us understand where that water is. Almost immediately after landing, they deployed the Pragyan rover. And they don't have a lot of time. The rover and the lander are only going to last for the next 2 weeks, one lunar day before the sun sets, the temperatures drop, and the electronics on board the spacecraft will fail. The rover is going to crawl around the area. It's going to be examining the regolith, trying to measure the mineral constituents in the soil, and try to get a better sense of how much of this water is mixed in, what other elements are there and available. So there should just be a flurry of news coming from this mission for the next couple of weeks, and then silence. Officials at India Space Agency hope that maybe the rover and lander could survive one lunar night. It'll be tricky, but we'll see what happens. But no matter what, they've got 2 weeks of solid science ahead of them right now to do before the sun goes down. Congratulations to everyone part of India's space program. They've gone to the moon. They've gone to Mars. They're working on sending humans to space. It's a really exciting space agency, and to see a lot of these developments coming from them. And I'm so glad that they were able to stick this landing. Speaking of landings, just a couple of days before, Russia's Luna 25 mission attempted a landing on the moon and failed. We don't know what went wrong. Apparently, its main engine fired for 127 seconds when it was only supposed to fire for 84 seconds. And so that would have put it into a bad orbit and definitely could have contributed to the crash. We're going to get more information from Roscosmos at some point, or we won't. But that mission failed. And that's too bad. I mean, this was the first time that Russia has attempted a mission to the moon in about 50 years. And following on the failure of the Phobos Grunt mission, they're not having a lot of success with any of their interplanetary work. Another image of the Ring Nebula from JWST. A couple of weeks ago, we shared an image of the Ring Nebula from JWST. And the Ring Nebula, this is a planetary nebula, one of the closest, brightest ones that we can see. And it's really easy to find in a small telescope. I'm sure many of you watching have seen the Ring Nebula through a pair of binoculars or a small telescope. That first image was taken with NIRCam, but the astronomers who took that image said that they had also used MIRI to take an image of the Ring Nebula, and this week they released it. Looks like a goat's eye or something. Anyway. And with the incredible resolution of JWST, you get just one of the most glorious pictures of the Ring Nebula that I've ever seen. Nothing like what I've seen through a telescope, which is just like this little faint, dusty donut. This is bonkers. Apparently there are 20,000 individual blobs of material in this image, just debris that came from the star as it died, each one with about roughly the mass of the Earth. There are these interesting spikes that are radiating outward from the ring, and apparently these are the shadows cast by the blobs of gas that are throughout the area. And what's really interesting about these regions is that in these shadows, the gas and dust that's contained inside is protected by the ultraviolet radiation that's coming from the dead star at the middle. And so they're able to form more complicated molecules and not get broken up the way the ones that are just getting hit by the ultraviolet radiation are. And so it's very interesting to sort of think about places in space where shadows protect organic molecules getting created. And you wonder sort of what role did that have to play in organic molecules finding their way to us here on Earth. And this is the possible fate for the sun. Billions and billions of years from now, when the sun finally runs out of hydrogen gas in its core as fuel, it will puff out its outer layers, switch to helium burning, expand, contract multiple times, and put out these shells of material. And some alien civilization will look at the sun and go, oh, look at that pretty planetary nebula. And that'll be us. Space junk, hit by space junk, creating more space junk. We talk fairly regularly about ways that we could clean up space junk. And one mission that's going to be tried in a couple of years is called Clear Space 1. And this is a mission that kind of looks like a four-armed spider? What's it? Claw from a game machine? It kind of looks like one of those claws from a game machine that will grab on with these four grabbers onto a piece of space junk. And the people behind the mission have already identified the target they're going to go after. It is the Vega Secondary Payload Adapter, which was part of a launch in 2013. And this is sort of the piece that fits between the top of the rocket and the payload. And it's still on the same trajectory as the payload, but it's just floating freely in space. It's a piece of space junk and is a risk to future missions. And so folks at the European Space Agency thought this would be the perfect target to try and grab onto and deorbit, cleaning up the environment. U.S. Space Force is tracking all of the space debris out in orbit, and they noticed that a bunch of particles had appeared beside this very specific piece of space junk. And they believe that a piece of space junk hit this space junk, creating more space junk. It's kind of ironic. And so the one target that they were going to try to go after to bring it down, to clean up space junk, they're too late. It already got hit by space junk. Now, this isn't a total deal breaker. ClearSpace says they can still launch, dock with this piece of space junk, bring it back down. But once they actually get in space in 2026, they'll be able to get close to the debris, analyze and see what happened. And it's kind of interesting to see like what happens to a piece of space junk over time as it gets hit by other debris. And what kinds of risks will that cause for any attempt? You can see like the clock is ticking. As soon as one of these pieces of junk is up there and any satellite, it's at risk to being struck by other pieces of debris. And so we really can't let this stuff sit around for too long in space. I feel like I've said the word space junk too many times. Space junk, space junk, space junk. It's like you say Beetlejuice. People ask like, when's the Kessler syndrome going to start? And it's not like it's going to be overnight. It's just going to happen bit by bit by bit as object after object are hit by debris, and that debris hits other debris, and the orbit just becomes more and more dangerous for spacecraft flying through. And it'll never be like this completely impenetrable shell that we just can't get out of. It will just be friction that every satellite risks being worn down by space debris and broken up. And anytime you attempt to fly through that, you're going to have to just take your chances as you pass through the region. Another way to measure the expansion of the universe. One of the biggest challenges in astronomy right now is the Hubble tension, to try to figure out what is the true expansion rate of the universe. And at the closest scales, astronomers get one number, and at the farthest scales, in the cosmic microwave background radiation, they get a different number. And their accuracy of both those measurements is so good that their error bars don't overlap. So what's going on? There's still the possibility that one of those measurements is incorrect, but the more exciting possibility is that there's new physics, that the universe did something differently, that maybe the expansion rate hasn't been consistent over time. Maybe there was a time early on when it expanded much more quickly and then slowed down. Maybe the acceleration is accelerating and that's going to lead to a big rip in the future. Like, we have questions and it's exciting. So astronomers are always looking for new ways to measure the expansion rate of the universe and also to measure how the expansion rate is changing over time. One of the main ways that astronomers measure the expansion of the universe is called cosmological redshift, where they look at thousands, millions of galaxies across the universe, and they measure how the light from those galaxies has been redshifted over time. The faster the galaxy is moving away from us, the more the light has been shifted into the red end of the spectrum. But this is all a snapshot. They look at all these individual galaxies and they measure their redshift, but they're so far away and they're going so fast that it's really hard to measure this changing over time. But if you could measure the expansion of the universe changing over time, and this technique is called redshift drift. And it's purely theoretical right now. Let me give you an example. Let's say you want to look at a galaxy that is 12 billion light years away. From our perspective, that galaxy is moving 95% the speed of light. But every year, its speed increases from our perspective by 15 centimeters per second per year. And so if you waited a few million years, maybe we'll get to 96% the speed of light, 97, and then 140% the speed of light. There are no telescopes that can detect this redshift drift today. It's just like it's too small of a change from year to year. But in theory, the upcoming extremely large telescope, this is this giant 39-meter telescope, it's going to be so sensitive that over the course of, say, 10 years, it should be able to measure the increasing redshift of galaxies that are really far away. And this will be revolutionary. But maybe there's a way that we can get this measurement early. A team of astronomers have proposed that you can use gravitational lensing to measure the redshift drift. We talk about gravitational lenses all the time. You've got this foreground galaxy cluster that is lensing some background galaxy. And if things line up right, then the light from this distant galaxy will take multiple pathways to come around the galaxy cluster and then to be visible from our perspective. The light has to take a different route around this galaxy cluster. And so you've got a way to measure the redshift of this galaxy that you're lensing multiple times. In each one, you're going to get a different measurement for the redshift. And so by measuring the redshift from all of these different versions, you will see snapshots in time of the same galaxy, and you can check the redshift drift. Now, I've got an interview coming shortly with Geraint Lewis, who is one of the astronomers behind this idea, but I was so excited about it, I just wanted to share it here first, and then we'll get a more in-depth interview in a couple of days. So maybe if we can measure this redshift drift, we can make some of the problems in the crisis in cosmology, the Hubble tension, go away, or maybe they just get worse, which is even more exciting. Every week, we do a vote on our community tab where you tell us what you thought was the best story of the week. And this week was a lot closer, but the story that you all liked the best was the most distant stars and the most distant galaxy seen by JWST. So thank you everybody for voting. Just remember, subscribe, and that way you have a much better chance of seeing this vote come up in your community tab. And when you do vote, tell us what you thought was the best story of the week. Neptune's clouds are disappearing. Astronomers have been watching Neptune with really powerful ground and space-based telescopes for about 30 years now, like the age of the Hubble Space Telescope. We got our baseline images of Neptune back in 1989 when NASA's Voyager 2 spacecraft flew by and saw a lot of features on the surface of Neptune. And then from that, astronomers have been able to watch both with Hubble as well as ground-based observatories like the Very Large Telescope or the Keck telescope to see how the weather changes on Neptune year after year. And what they found is that the amount of clouds on the surface of Neptune seemed to rise and fall over time. And it's weird to have it be affected by the seasons because Neptune receives about 1/900th the amount of light from the sun that the Earth does. But there's some preliminary results that say that in fact the weather on Neptune is somehow affected by the solar cycle that seems to follow the sun's 22-year solar cycle where it goes from solar maximum to solar minimum and then back to solar maximum. And we get different amounts of stellar wind coming off of the sun, as well as different amounts of sunspots, coronal mass ejections. And so there could be some kind of connection between that. And I'm here wondering, like, is there some kind of connection between Earth and the sun's solar cycle? I promise you, astronomers have looked into that, and the answer is no. And in another set of images that just came out from the European Southern Observatory, we got evidence that the dark spots on Neptune are back. Now, a dark spot was first seen on Neptune, again, back with the Voyager 2 spacecraft. And then after it left, astronomers weren't able to see these dark spots. And so they assumed that they kind of come and go very rapidly. They don't last very long. But in a new set of images, they were able to see one of these dark spots on Neptune. So it's believed these are caused by air particles in the atmosphere of Neptune darkening the layer below in the main visible haze layer. With so many instruments able to watch Neptune on a regular basis, every time it gets closest to the Earth in its orbit, we get the best images that we can. You could add on top of this images from JWST. We're going to be able to watch how the atmosphere changes at Neptune from year to year and try to figure out what the connections are to its interaction with the sun, its seasons, whatever seems to be causing its weather patterns. Now, if you like the work that we do, why don't you consider joining our Patreon? This is a way for our fans to directly support independent space journalism. We're able to produce over 100 articles on the Universe Today website every month, a dozen videos, podcasts, all kinds of great space content, and we make this freely available. Creative Commons 4.0 license, so anyone can use, remix the content that we create. And this is only possible thanks to our patrons. Now, if you become a patron, you get some other benefits. We will remove all the ads from the Universe Today website for you for life. Even if you stop being a patron, you get behind the scenes information. You get a special patron-only podcast where I answer your questions in too much detail. And you get to directly support the salaries of people who are masters of space science journalism. So go to patreon.com/universetoday and join our Patreon community. An actual exoplanet orbiting a star for 17 years. Almost all of the exoplanet discoveries that we have made so far are using various indirect methods. So you use the radial velocity method, where you measure how a planet is yanking a star back and forth with its gravity. Or you measure the transit method, where a planet passes in front of its star and darkens the star momentarily. Or gravitational microlensing, where a planet passes in front of a star and distorts the star with its gravity, and you detect that the planet is there, but then it's gone forever. But a few planets have been seen directly with telescopes, and the most famous of these is Beta Pictoris b. Astronomers have been watching this planet orbit around its star now for 17 years. And we got a new video. It's about 11 seconds long, and you can watch this planet orbiting around its star. And this isn't just like an artist's impression. This is the actual planet orbiting the actual star. We're really at the very beginning stages of direct planet observations. You need the right circumstances. You need a planet that is big enough and far enough away from a star that it can be imaged in a large telescope. It needs to be in the right orientation so that we can see it, seen face on. You can actually watch it going around the star. And you need the right kinds of instruments on board your telescope. You need a way to block the light from the central star so that it can reveal the much fainter planet. And you get all this in Beta Pictoris b. This is just preparation for what's going to be coming next when, say, the European Southern Observatory's extremely large telescope comes online. It's going to be a much bigger telescope, much more sensitive, and it's going to have all the right instruments on board to show off this kind of thing. In theory, it'll be able to detect an Earth-sized world orbiting around a sun-like star, but it should reveal many planets orbiting around their stars, directly imaged. So enjoy this video and just think about what's coming in the future. Now, earlier on, I talked about how the Hubble Tension is about to get more exciting, and I'm going to rant about that in a second. But first, I'd like to thank Joel Yancey, Antonio Lofilara, Dustin Cable, Just Paul Davis, Vlad Shiplin, Jay Dennis, David Giltonad, Modzo, George, Jeremy Mattern, Jordan Young, Tim Whalen, Dave Verbeoff, Andrew M. Gross, and Josh Schultz, who support us at the Master of the Universe level. For the last couple of years, as I've been interviewing astronomers about the Hubble tension, about the crisis in cosmology, you really get a sense of how excited they are that there are these gaps in their knowledge and their understanding. That you get this expansion rate of the universe at one point in time, and it is very different from a measurement that you make at a different point in time, and their error bars don't overlap. This is the crisis in cosmology, and they're really excited about this because when a model is too complete, then you don't have a lot of place to make progress. And astronomers know that the Big Bang model of the universe is incomplete. There are problems that are solved by the inflation model, but they know that there are places that they need to be able to figure out how things came together, how things evolved over time. Why do we get the universe that we see today? Why are the amounts of matter and antimatter different? What is dark matter? What is dark energy? They have all these questions. And it's really hard to make progress on those questions when everything lines up too nicely. And so to have this thing that is glaringly different is really exciting. And that's why I share a lot of stories about new ways to measure the expansion rate of the universe, because the Hubble tension is one of these places where there's like this little glint of sunlight coming through that astronomers want to try to be able to focus on and try to open it up and figure out what's going on. I get a lot of comments here on the channel where people will tell me like, oh, astronomers think they know everything, and they don't. And they are so excited when there are places that show them that there are mysteries and they don't understand how things are working. And although the term is a crisis in cosmology, you would think that's a bad thing. But when I talk to astronomers, they couldn't be happier with a crisis. And because anytime you find something that you weren't expecting, it's exciting. And so we are going through, I think, one of the most productive times in the field of cosmology, in astronomy, astrophysics. We are learning new things about the universe, and every day we learn a little more, but then we have even more questions. And I'm so grateful to be around as this is happening. So stay tuned. We don't know how the story ends yet, and that's what makes it so fun.